our next speaker is Miranda Cheng from Harvard University, and she'll be speaking about M24, K3 string theories, and Monstrous, holographic moonshines.
Can you hear me? Is it on? Okay. So I'll start by thanking the organizers for the invitation, and it's a pleasure to be able to speak here. And so in the past few days, we have heard a lot about the interaction about string theory and math, but in particular, I think it's more about string theory and geometry, and not so much about string theory and, for instance, number theory. So that explains my choice of topic. And also, we have seen that ADS-CFT has played a very, very important role in physics, but it hasn't played so much role in the interaction with mathematics. So I decided to use my slots to present some work that might be a little step in filling this hole of string math landscape. And so hence my title. And before I start, I'll just give a very short summary for the orientation, like what this is all about, more or less. The Moonshine phenomenon describes an unexpected relation between sporadic groups and modular objects, as we know. And it has been one of the most exciting developments, arguably, in mathematics in the last century. And yes, it's the last century now. We're in 2000. So, and particular string theory has proven vital in the understanding so far in such a connection, for instance, in the most famous Monstrous Moonshine. And actually, last year, a new Moonshine with many actually very novel features have been proposed. And this time, the sporadic group in question is the largest mature group, M24. And we'll see how string theory, and not just CFT, but also non-perturbative string theory, compactified on K3, ties various automorphic objects together with conjectural M24 symmetry. And as I said, since we have heard a lot about geometry, so although there are many interesting geometric aspects to this story, but I'll majorly skip them. So more focus on, the automorphic forms and number theory aspects of the story. And finally, I want to argue that we can demonstrate how ADS-CFT considerations provide natural explanations for some of the crucial properties of the modular groups that appear in all the known Moonshine story. Okay, so the outline of my talk is the following. I'll give a rather long introduction to the relation between automorphic forms and string theory, and a shorter overview of just to remind you what sporadic groups are and what Moonshine is. And then I'll talk about the relation between M24 and all kinds of automorphic forms that you get when you compactify type 2 string on K3. And in the end, I hope I'll have time to talk about some work in progress with John Duncan on the modularity properties of the moonshines and why ADS-CFT, we argue, can help us to understand them. Okay, so first the review part, automorphic forms in string theory. So string theory is very good at producing all kinds of automorphic forms. So because we have all kinds of symmetries that can be realized in string theory, no matter whether it's Walshy symmetry or space-time symmetry, as long as it's a symmetry to the problem, if you have the appropriate counting object, then the symmetry should be realized. And so that's fair enough. And then let's see some interesting examples. The first example is just when you consider CFT, just a bosonic CFT, and you compute the partition function. And on the left-hand side, you have, this is the definition in the Hamiltonian formalism. You're just basically, you have a Hilbert space, and then you want to count your dimension of the Hilbert space. And you have a natural grading of your Hilbert space in CFT, which is given by the L0 of Virasoro quantum number. So since it's chiral, I'll write the Hamiltonian as replacing the L0. And then on the other hand, on the Lagrangian side, you can write it your partition function as a path integral. So you're summing maps from a torus with complex structure tau to some targets So where it's the x of d is where your fields live. So from the so from this consideration, you see that on the left-hand side, you naturally get the Q series. On the right-hand side, you naturally get something that is modular under SO2Z by definition. So that's how from CFT you can get a bunch of modular forms. For instance, the simplest example is just 24 chiral bosons, and your partition function will just be given by the 1 over eta to the 24. So eta is the Dedekind eta function. And this is nothing but the partition function of the chiral half of the bosonic strings, because 26 minus 2, which are the two Lycon directions, is 24. And because so now let's remember that it's also the supersymmetric partition function of the heterotic string, because on the supersymmetric side, everything is on the ground state. Okay, so let's move on to a slightly more complicated example. When we get not the modular form, but did I say Mach? No, not the modular form, but the weak Jacobi forms. Okay, so when you actually have a supersymmetric supersymmetric conformal field theory. So for instance, if you have n equals 2, 2 supersymmetry, then you have two copies of n equals 2 superconformal algebra. For instance, one example of such a conformal field theory would be 2D sigma models with a Calabi-Yau as a target space. Okay, so now you have a little bit more conserved currents, not just the Virasoro, but you also have the U1 currents, and you can use them to grade your Hilbert space with finer information. That's why now we not only get the Q series, but the Y series. And an interesting object is the so-called elliptic genus. So basically, you're computing the right-moving Q cohomology, because if you look at the right-moving side, it's nothing but the equation that Davida just wrote down, counting the Witten index, but the left-moving side can be anything. Okay, so so one thing to keep in mind is that this n equals 2 superconformal algebra, the n equals 2 supersymmetry basically stems from the scalarity of your target space. So if you have a hyperkähler target, actually you will have n equals 4 superconformal algebra rather than n equals 3, n equals 2. So since we're talking about K3, that's going to be important later. Okay, so as I said, before that these conformal field theory objects naturally have SO2Z invariance, but now we also have actual invariance because we have n equals 2 now superconformal algebra. So using these considerations, you can predict that this elliptic genus that I just wrote down in the last slide is actually a weak Jacobi form of weight 0. What it means for our purpose is that they transform nicely under this Jacobi group and have the expansion in this way of the QY expansion. In particular, the Fourier coefficients only depends on this particular combination of the two quantum numbers. Okay, so that's yet another automorphic form you easily get from conformal field theory. Okay, we can get even more interesting non-trivial automorphic forms when we go beyond perturbative string and actually consider non-perturbative string theory. So in order to introduce that, let's have a little interlude first. Okay, so let's consider some special situation when your target space actually has some automorphism group. I call it the big G. And then when it is the case, then there are naturally two things you can do. The first thing is the following. Since the target space has this symmetry, the Hilbert space should also has this symmetry. In other words, your CFT Hilbert space now is actually a representation of your group G. So instead of just computing the dimensions of your Hilbert space graded by this graded by the Hamiltonian, you can now also compute the characters of your Hilbert space by inserting an element of the group, just computing the character of the representation. That's all you're doing. And this is what we call the twisted partition function. And again, it has a simple expression in terms of the path integral. Now you're just changing the boundary condition of your path integral in this way. Okay, so there another thing you can do, which is you can consider now orbifold CFT on this space. And this orbifold CFT has the nice property that its Hilbert space is decomposed into the decomposed into Hilbert subspaces that are labeled by the conjugacy classes of your group. This is because, well, if we just consider a loop space of this, then it naturally decomposes in this way with this kind of boundary condition. While phi is the map from S1 to the original target space X. So you can also compute now the dimension of your Hilbert subspace in your orbifolded theory. Okay, so you can pick out your Hilbert subspace labeled by conjugacy class H, and in this way, and it gives a twisted sector partition function. That's what we call it. And then again, it corresponds to a change of boundary condition in this way. Okay, so that's a natural thing you can do when you actually have an automorphism of your target. And one thing about the automorphism property of these twisted guys is the following. Because, again, from the torus picture, we know that when we actually apply a SO2Z transformation, now we not only change the complex structure, we are also changing the boundary condition. So in general, they won't be SO2Z invariant anymore. They will be invariant under some other group I call gamma G. Okay. Okay, so now let's go to string theory beyond CFT. So to do that, okay, let's think about take an example of symmetric products. Take your target space now to be a symmetric product. And so now the group of automorphism will be just the permutation group. So the Hilbert space is labeled by these conjugacy classes. We call it the winding number. For instance, this picture shows a winding number 243 in this picture. So just from this picture, you can see that the generating function of the elliptic genus of the CFT on the n-symmetric product of your space can be written as a second quantized string partition function, now with one more dimension in your compactification manifold. Okay, so then from this definition, you can write down an explicit formula. So this is an explicit formula in terms of infinite products. And these exponents will be just given by the Fourier coefficient of your original single copy elliptic genus. Okay, so yeah. So what does it have to do with automorphic forms? It has been shown that these guys are actually almost automorphic. So this you have to multiply with some small factors that is called the Hodge anomaly. It's called the Hodge anomaly because it's determined purely by the Hodge numbers of your Calabi-Yau. Okay, and right. So in other words, you get from the data of a weak Jacobi form or a modular form in general, you get from it something that is larger, that is automorphic under a much larger group. Okay, so basically you can think about it as adding a 1,1 unimodular lattice to your story by further compactifying down. And so this is true for all Calabi-Yaus. But when your Calabi-Yau is K3, then this Hodge anomaly factor, this prefactor here, actually has a very nice physical interpretation, because then in that case, this factor basically just corresponds to a further compactifying down, so one more dimension. So this automorphic form, in other words, actually counts the BPS index, which preserves the quarter BPS supersymmetries in type 2 string on K3 times T2. So so this is the expression here. And yeah, and just a comment here is that this automorphic form is one of the few that is actually extremely nice, because it turns out that it's also a denominator of a generalized Kac-Moody algebra. In other words, this automorphic form defines for you a generalized Kac-Moody algebra, because it has both infinite sum expression and a non-infinite product expression. It's particularly nice because, well, the denominator of a generalized Kac-Moody algebra is very often an automorphic form, but not another way around. So this is an automorphic form that is particularly nice from that point of view. So now just, okay. So now, let's just wrap up the story. Now, since I'm talking about type 2 on K3 times T2, and from what we learned in the past many years, including the talks of this morning, we know that, well, quarter BPS states and half BPS states cannot be totally disconnected because we can have two center bound states of like each with half BPS charges, and they can form a bound state which preserves quarter BPS. So you should also be able to find half BPS states degeneracies in your quarter BPS states counting formula. So this is indeed true because, okay, half BPS states in this theory from the duality, as we said earlier, is counted by nothing but 1 over eta to the 24, simple enough. And then these two center bound state BPS states can be found in the partition function of quarter BPS states by looking at the poles. And indeed, the poles behave in this way, and it reproduces for you the correct index for these two center bound states. Okay, so to summarize my review, now we have this web of automorphic objects by considering K3 compatified string theory. Okay, so here we start with the weak Jacobi form, which is the elliptic genus of K3, and we can lift it, and we get a bigger automorphic form, which has a physical interpretation as counting quarter BPS states. And then when we look at the poles, we get back the modular form, 1 over eta to the 24. So these are connected in this way. Okay, so now I'm going to switch gear. Unless there are questions, I'm going to talk about sporadic groups. Okay, so so this is, of course, a review. Now, first of all, what are sporadic groups? There are 26 finite simple groups that don't fall into infinite families. So in other words, they are sort of the misfits of sporadic groups. I don't know if there are fans of misfits in the audience, but I am. But so in this diagram is the subgroup structures of these 26 sporadic groups. And there are two famous misfits in this family. So one is the biggest one, that is the monster, because it's the biggest and it contains the whole happy family here. Well, the happy family is actually a technical term, but believe me or not. It's true, they are called the happy family. So so it's gigantic. The order is like order 10 to the 54. And the other famous guy is the largest mature group, which is called the M24. It's because these 5 mature groups are actually the oldest in the family. So they are discovered in the, I think, 1830 something. Okay, so sometimes, occasionally, the misfits are actually particularly pretty, as in this case it turns out. In this case, so these sporadic groups enjoy the so-called Moonshine phenomenon, which refers to a relation between a sporadic group to modular objects. In particular, in more details, if you pick out any conjugacy class of your sporadic group, you can associate with it some object that is modular. That's the general idea of a Moonshine phenomenon. So now let's go through one simple example, since it's famous. Okay, so it's not simple. Oh, it's not simple. Okay, so let's go through some not simple example because it's famous. And so let's look at the Klein invariant, which has this expansion. And so, okay, fine, it's a Klein invariant. It's very nice. But then we have the very famous McKay equation, which says 196,884 equals 1 plus 196,883. So why is this why is this equation so famous? Because because these numbers in red are actually also happen to be the dimensions of the irreducible representations of the monster group. So in other words, it is as if there exists an infinite dimensional M representation with a Z grading such that the dimension of each Vn is also the Fourier coefficient of the Klein invariant. Well, this is extremely mysterious. So, but let's finish the conjecture. Okay. So if this is true, then we can again also compute the character of the representation, not just the dimensions. So so we will get some other Q series in this way for each conjugate class of the monster. So they're called McKay-Thompson series. And so the Moonshine conjecture says that all these guys are actually invariant under some Genus 0 subgroup of SO2R. So Genus 0 refers to the genus of the compactified fundamental domain of your modular group. Okay, so the big question is the following. So what do the sporadic groups have anything to do with modular forms? Because they belong to traditionally very different subjects. And a partial answer, I won't call it a full answer, but the partial answer is given by conformal field theory. So it turns out that these representation of monster is basically a Hilbert space or of a chiral CFT with a monster symmetry. So in particular, this Z grading that we see is nothing but L0 eigenvalues of your quantum states. And these McKay-Thompson series then have the interpretation of twisted partition function of your conformal field theory. In particular, the partition function itself is basically your J invariant. And it has been proven by Borchert by introducing the concept of generalized Kac-Moody algebra and considering the automorphic lifts of, from these modular functions to automorphic forms phi of G. And this lift, again, has the physical interpretation of going beyond CFT and going to non-perturbative, going to a string theory, okay? And in other words, this is the paradigm of the Moonshine phenomenon. You start with a sporadic group, and from the Moonshine, you get to modular objects. And then from these modular objects, you can lift it to an automorphic forms under some larger group. And these automorphic forms would turn out to be the denominator formula for a certain generalized Kac-Moody algebra. And the root system of this generalized Kac-Moody algebra will have your sporadic group as a symmetry. That's the paradigm, okay? So now, after a long review, I think I can start talking about M24. Okay, of course, this is still a review. But let's get to the real protagonist of the story. So the name M24, 24 comes from the fact, you can understand it by the fact that you can think about M24 as some subgroup of S24. So you're just permuting the group of permuting 24 objects. So in this representation, associated to a conjugate class is also a frame shape in the following way. For instance, the identity element, the frame shape is just 1 to the 24. It denotes a 24 set of elements with 24 sets with one element, so you're permuting basically nothing. And there are order 2 conjugacy classes. One has this frame shape, so it leaves 8 elements fixed while permuting the other 16 as 8 pairs. And the other one has no fixed point. It just permutes 12 pairs. Okay, so that's one way to understand, to know, have some idea about the property of M24. The other one is it's an automorphism of something, and there are 24 Niemeyer lattices, as we know. So a Niemeyer lattice is something, a lattice that is 24-dimensional, self-dual, even, and positive definite. And just like Monster is a symmetry of the Leech lattice, and M24 is a symmetry of another less famous, so we don't have a name. We call it N, okay, another Niemeyer lattice. And from this fact, actually, it has been shown quite a while ago that all automorphisms of K3 surfaces preserving the hyperkähler structure actually have to sit inside M24. So that's sort of a first hint of a relation between M24 and K3 surfaces. Okay, so now let's talk about well, the new developments. Let's see how much time I have. I have 15 minutes, right? So a bit more than 15 minutes. So okay, then I think I have to skip some things. So okay, so let's just look at the elliptic start with the elliptic genus of K3 surfaces. So the elliptic genus that we have talked about much earlier. So this elliptic genus has been computed a long time ago, and it has a very explicit expression. And we can also rewrite it in this way, okay, in this as the second line. So the motivation is very clear why we want to rewrite it in this way, because all these numbers are actually counting the number of n equals 4. Okay, there's a typo here. N equals 4 superconformal algebra representations. Well, the idea is extremely clear because, as I said, the target is hyperkähler, so we have n equals 4 superconformal algebra. So the elliptic genus has to come in families of superconformal algebra representation characters. So so that's why when we want to know how many of a certain kind of representation there are, so we just decompose it in this way. So we get this Q series here that encodes for us the number of n equals 4 representations with a certain quantum numbers that are appearing in this elliptic genus. Okay, sorry. So this is a large sum. I didn't write down the expression, but it's also a Mach thing. It's an upper large sum. Maybe you have seen it with two parameters u and v, but this is u equals v. Okay, so it turns out that these Q series encoding all the numbers of massive n equals 4 representations, they are actually it is actually a weight half Mach modular form. So a Mach modular form is something that is almost a modular form, but not quite. But yes, that's all we need to know for the purpose of this talk. And so the amazing observations made by these people, and including someone here, is that these numbers are also actually dimensions of irreducible representations of M24. So again, the observation is that it is as if we have M24 module K such that this Q series is doing nothing but counting the dimensions of this module, this M24 module. So now we can do the same game. If this module actually exists, then again we can also compute its characters, not just the dimensions. So we can compute this guy. And then just as before, because it comes from a CFT kind of consideration, so we expect it to transform under some group, some subgroup of SO2R as, again, a weight half Mach modular form. Okay, so that is sort of the logical consequence of the assumed existence of this M24 module in the elliptic genus of K3. Okay, so the status is that all these mock modular forms, indeed transforming under some subgroup, have been proposed for all the conjugacy classes of M24 last year. Okay, so let's formulate it better. So the conjecture is that all these weight-half mock modular forms that are provided for you in the papers that I just cited on the last slide actually have some underlying M24 module K of it, and it has passed many checks. One is just by brute force constructing these modules for each grading, and the second one is more geometrical. Is that when this G actually generates an actual symmetry of your special K3 surface, then the whole Hilbert space has to be a G module, and you can actually compute the elliptic genus, the twisted elliptic genus. And this computation has been done by these people, and then what they got indeed coincides with what we got from just modular form kind of computations. So, okay, all we need to know is that I bet with you that it's true, and we can move on. And so, okay, I don't want to go into details here, so let me skip this and just tell you this. So, okay, so after that conjecture, which is basically the orange line here, so what I thought is, okay, I should complete the diagram of Moonshines and see if it falls into the usual paradigm of Moonshine. So using this orange as an assumption, so I could do the other blue thing here. So indeed, I know that there is already a generalized Kac-Moody algebra for me, and then I can compute the twisted denominator, assuming that the Moonshine holds, and then I can check that these mock modular forms here, or the weak Jacobi forms if you want, and the twisted denominator phi of G, which are automorphic, are again related by a lift. And this consideration leads to new conjectures about new automorphic forms phi of G, and a part of it, so this conjecture has been shown for some of the G's, and for the rest it's work in progress. So this is like kind of work that has been done by Clary and Grisenko, and it's being generalized to hopefully to prove the automorphism properties of these twisted denominators. But we also have seen this nice triangle of modular objects before. So we not only have weak Jacobi forms, in the triangle we have also seen the modular forms given by the Euler functions, and these automorphic forms here. So if this Moonshine is true, I could also extend that triangle to now not just the old ones, but for a new one for each conjugacy class. So, sorry. So yes, so now I combine the two diagrams in this way. So indeed, I have a set of modular forms given again by complicated expression, or not so complicated expression of eta functions. And then again, they're related to the new, presumably automorphic forms with the pole condition, which is motivated by the physics of multi-center bound states of physics. And then this yellow line is the second version of Moonshine, which actually is proven, unlike the orange one, which is still now a conjecture. So this summarizes the work of myself and other groups of last year, basically to complete this diagram. And many bits of it, most of it are still conjectures. So there's a lot to be proven and a lot to be learned about geometry. But now I'm going to talk about something else. So now I'm going to talk about my work in progress with John Duncan. Hopefully it's going to come out rather soon. And Okay, so first of all, I should tell you what is the problem that we're trying to solve. So in order to do that, I have to tell you in more detail what the genus zero property of other moonshines are. So one thing to know is that genus zero subgroups of SO2R are rare. There are many subgroups of SO2R that are, that are discrete and commensurable with SO2Z, so they could, in principle, all show up as your modular group for your twisted partition function and whatnot. But the observation is that they have to all be genus zero. So it went back even before the moonshine. It went back to the famous Jack Daniel that is offered by Ock in '73. So what he observed is the following. So there's a particular kind of congruent subgroups of which we'll call gamma 0 p plus. So for any positive integer p, you can define such a group. And then they asked the following question. So what are the prime numbers p such that these kind of groups are genus zero? And the observation is this list of prime number is the same as the list of prime numbers that divides the order of Monster. So remember that the order of Monster is that this 10 to the 54, a huge number. It seems quite rather striking that these two lists are the same. So he offered a bottle of Jack Daniel to anyone who can explain that. And then there has been a sort of an explanation by Monstrous Moonshine, because we know that an essential part of the Monstrous Moonshine conjecture is that all the groups are genus zero. So then at least it implies that it has to be, it has the number p has to divide the order of the moonshine. Okay, so this genus zero property has been generalized to the so-called generalized moonshine and other sporadic groups, the moonshine of other sporadic groups, and including something that are not in the happy family, has nothing to do with Monster. Okay, so this is sort of a golden rule in moonshine, if you want. But why? I mean, still, it's rather mysterious why this is so. And even worse, so after this M24 business came along, so me and my mathematician friend John Duncan decided to look at the genus zero property of this new moonshine. What we expected to find is that we would just compute the groups and look at the list and compare and compute the genus, and then voila, they're all genus zero. That's what we expected. But no, I mean, we actually didn't find any genus zero property. We tried everything, like, adding etas and thetas, dividing, multiplying etas and thetas, but we never got the list that all the modular groups are genus zero. So we concluded that it's just not true just by inspecting, these numbers we got. It's just not genus zero, so it's heresy, but it's true. So we were completely stuck. So until we reminded ourselves that, at least some of us should know a little bit of physics, and as a modern string theorist, if you have a CFT problem you cannot solve, then the intuition, the reflex should be that then you just do ADS. So how did that work? So let's recall that the ADS. Now we have a CFT2, so it's a CFT2 and ADS3 correspondence. So let's recall that, well, in 3 dimensions, ADS gravity is extremely simple. So in particular, the saddle points are all labeled by some modular groups or modular subgroups if you have some twisted boundary condition on the boundary. And if this is true, okay, and if we assume that the CFT we care about has a semi-classical or semi-classical-like ADS gravity formulation, then your partition function or twisted partition function and whatnot should also be computed from the gravity side. And since it's semi-classical formulation, it should be computed by the saddle point approximation by summing over saddle points. So in other words, your twisted partition function should be Rademacher summable. A Rademacher sum is basically if you take some function of tau, and then you sum over the modular orbit, and then regularize it and get something finite. And then that's the idea of a Rademacher sum. And in your ADS-CFT context, it has been explored in this paper before. And okay, so the Rademacher sum basically goes like this, as I said. So if you take some function of tau, and then you just sum over the orbit. And this is manifestly invariant under gamma g. But the problem is, most of the time, it's just not convergent, so you have to regularize it. Okay, and we define the concept of Rademacher summability by saying that you can find a regularization scheme such that this Rademacher sum is convergent and is anomaly free. Because usually what you get is you get something convergent, but the regulator will break the symmetry, so you get on the right-hand side something that is not invariant under gamma g anymore. So an example, famous example, is by Rademacher. You can rewrite the Klein invariant in this way. So you see there's a regularization here. And you have to subtract the contribution at tau to I infinity here at the cusp. And so now let's step back and assume Rademacher summability of your partition function and see what kind of conditions you will get. And then the interesting thing is that for the cases that your partition function is a modular function, and Rademacher summability is if it holds if and only if your group G is of genus 0. So okay, so that's a reasonable assumption with reasonable results that is compatible with other moonshines. So now let's look at our case. So in our case, our counting function is just not a modular function. It's actually a weight half Mach modular form. So when the weight changes, the condition of Rademacher summability just changes. And now the genus 0 condition and the Rademacher sum condition just decouple with each other. So the left-hand side doesn't imply the right-hand side anymore. And what we did was then, okay, we just check whether these guys, instead of checking whether they are genus 0, we just check whether they are Rademacher summable. Indeed, using the results of other people, then we can show that all the lists we got can be rewritten as a Rademacher sum. So this is the assumption this was the assumption we made from ADS-CFT, and then it passes through all the checks, including an M24 case, and it covers if and only if, on the if and only if basis, the known Moonshine modularity condition. So to summarize, all the known Moonshine theories of Moonshine have a CFT origin, or vertex operator algebra origin, if you like. So if now we make the assumption that such a theory has a dual description, then all our McKay-Thompson series have to be Rademacher summable. And for the modular function case, it implies only if the modular group has genus 0. And in our case, we don't have modular functions. We have some other kind of modular objects, and we just check that indeed all these Mach modular forms can be rewritten as Rademacher sums. So I think the Rademacher summability is a plausible replacement for genus 0, and it has a much better physical origin. So maybe we can have some whiskey for physicists instead. And then, well, ADS-CFT has many use in all kinds of other fields. We have ADS-CMT, condensed matter theory. We have ADS-QCD. Maybe we should have some ADS number theory or in the ADS math. And thank you.
Any questions?
That's a very good because So, okay, the precise statement is the following. It's a little bit stronger than actually what I said. So, Rademacher summability for k equals 1 implies genus 0, and genus 0 implies Rademacher summability for all k. K is, the central charge. So you can imagine. So this has nothing to do. Let's talk about the monster case. It has nothing to do with pure gravity and so on. So you just take the symmetric product CFT, for instance, and you have large central charge, and then the partition function has to be rewritten as a Rademacher sum. And
I mean, in K, I can understand you can take a symmetric product and then it's both something dual.
Yes, in that case, that's not so much of an assumption. It just follows from.
So that essentially, I can take it with just asking somehow the genus zero from each, not genus zero, but mathematical summability, the carried over that we use it in the product.
Right. Exactly. Yes. Yes. That is true.
So the symmetric product automatically is mathematically summable only to the original.
Yes, that's a genus 0k. In the genus 0k, that's the same. As I said, for the smallest central charge possible, so you just start with q minus 1, the original, the original Moonshine CFT. Okay, those guys are Rademacher summable if genus 0 property is satisfied. But genus 0 property tells you that all the higher central charges guys are all Rademacher summable. Does that make sense to you?
I'm not sure which other guys.
Okay.
Some conjectural CFTs which have Monstrous CFT.
Yeah, for instance, if you take the symmetric product CFT.
The symmetric product CFT of the
Monstrous.
Monstrous CFT, why do we have no?
I don't know. It's an assumption. I mean, it's a chiral CFT with a large central charge.
Move on to another question. Ron?
So, saying that the curve is genus 0 is the same as saying that it's Jacobian and Chiral. It's, for these Rademacher summability cases, can be interpreted by, is this a natural cover of the group and then somehow the twin is together? That
You mean why the Rademacher summability implies genus 0?
is it a geometric interpretation of what this Rademacher summability? Does it mean that something you manufacture out of the curve purely geometrically is going to be zero-dimensional?
Well, I don't know. I can tell you that the space of possible anomalies will vanish if you have genus 0. But that's probably not what the.
No, but usually you're saying that the genus is not 0, and yet.
If the genus is not 0.
Can you interpret geometrically? Is there something else that needs to be 0 in the case?
Something else than other than the genus, you said. Well, I just gave you another way to, like, the space of the anomaly has to vanish, but that's probably not geometric enough. I don't know. But there's probably some nicer way to think about it. I don't know.
Other questions?
You mentioned quite early on that you had this n equals to 4 superconformal algebra, and then you kind of compute the genus on K3, right?
Yeah.
And then you're counting states in a Q-bar cosmology, right? This Q-bar is just one supercharge or a combination of some of the four
The
supercharges?
Q-bar is the Q-bar of n equals 2 superconformal algebra.
So it's not the sum of two supercharges, but one of the two n equals 2?
Yeah, one of the two.
Is there a physical representation of the genus 0 curve that you mentioned at the end? I didn't really get that. Is there a physical manifestation of this curve as something like a rotary? Is that what's the physical?
No, that's really, I mean, you can think about a modular function as the a map from the fundamental domain to a complex plane. So in that case, the genus 0 has the property of, like, you're just mapping CP1 to CP1.
So it's like an auxiliary curve that you use it to get some information, but there's no physical.
Well, you can think about it as the space of complex structures. of your underlying torus, worksheet torus.
Other questions? Okay, let's think.